In this video, we're going to look at two questions on the electromagnetism. Okay, so first of all, it says a closed wire loop in the form of a square of side 4 centimeters is placed with its plane perpendicular to a uniform magnetic field. So I'm going to draw a diagram first, so a basic one. This will be a plane with side length 4. I'm going to write it over here. So 4 centimeters, and then essentially it's perpendicular to a uniform magnetic field, so something like this. Yeah. And then right angles. Okay, so and it gave us the rate of change of the magnetic field, and then the loop has a resistance of 2 times 10 to the minus 7 ohms. And then the question wants to calculate the current induced in the loop and explain with the aid of a diagram the relation between the direction of the induced current and the direction of the magnetic field. Okay, so first of all, what I'm going to do is calculate the current. Okay, so how do we calculate the current? First of all, one equation is that the voltage induced is basically equal to minus the difference in the magnetic flux, which is the difference in the magnetic flux over the difference in time. Now the magnetic flux is basically equal to the magnetic flux density times the area. Now in this case, the area doesn't change, it's only the density, so that is a difference in B times A over difference in T. And yeah, okay, so then we can further simplify this, so that will be a difference in B over difference in D. That will be just what is given, that's essentially the rate of change of the magnetic flux density, and then times the area, and that will be 0.04 squared because it's a square over here. And we can calculate the voltage induced. I'm not going to add the negative sign because it's only an indication of direction. Right now I just want to calculate the magnitude. Okay, so over here we have times 0.04 squared, so that will be I'm going to say 4.8 times 10 to the power of negative 5. That's volts. Okay, so that's voltage, and we are given a resistance, so therefore we can just calculate the current. So V is equal to IR, so I is just equal to 4.8 times 10 to the 5 negative 5 over the resistance, which is 2 negative 3, and that will be equal to, I think you can calculate this directly, so that will be 2.4 times 10 to the negative 2. So yeah, so that will be 0.0024 amperes, and that will be the answer to one of the question. Okay, so the other question that is asked is the relation between the direction of the induced current and the direction of magnetic field. Okay, so first of all, in order to do this, what we have to use is Fleming's left-hand rule, but in this case it's a loop, so and it's the induction of current, so we can use the reverse of the right-hand rule. So it says as with the aid of a diagram, so I'm going to draw a diagram over here. I'm going to say like this is the loop, okay, and then the magnetic field is going into the loop, indicate as crosses, and then essentially utilizing the reverse of right-hand rule, we would say that the induced current would be in the anti-clockwise direction. So the current induced will be in this direction. And then I'm not going to write a text, okay? So that will be answer to the second part of the question. Now, let's see the next question over here. It says a mixed beam of deuterons, and then he gave us the nuclide notation for it. So that is with a mass number of 2, and then with a positive charge. Okay, and then it says, and protons. So there's deuterons and protons, which have been accelerated through a voltage that is 1 times 10 to the 4, enter a uniform magnetic field of 0.5 teslas in a direction at right angles to the field. So I suppose this is, okay, so there must be some kind of circular motion, or because it's in right angles to the field, so it won't be an, I would say like a helical shape. And then it says to calculate the separation of the proton beam from the deuteron beam, which each has described a semicircle in the field. Okay. First off, I'm going to draw like a simple diagram to basically, I would say, visualize the system. So it will be something like this. This is the magnetic field, and then essentially there's a beam. Okay, so in the beam there's like the deuterons and protons, and I'm going to write like a red pen for the deuterons. So over here it says for the isotope of hydrogen it has 1 positive charge. If it has 1 positive charge, it's the same as protons. So the major difference is just the mass. For protons, it's just its mass will be 1 atomic mass, and then for this it's 2. So let's see. In this case, BQV, so the magnetic force they experience will be the same because they have the same charge. So therefore, the radius will be larger for the one that has a larger mass. So for the deuteron, it will go something like this. And then for the proton, it will have a smaller radius. And then what we want to calculate is just distances. And also they bend towards the same direction because they are both positive charges. Okay, so now let's see. The equation we are going to utilize is it didn't mention any speed. Okay, so what we want is the radius. Well, it gave us the voltage, and with the voltage, yeah, with voltage we can calculate the speed. So there's 2 equations we have to utilize. First one is just QV is equal to half mv squared, and then the second equation is with the velocity you can utilize mv squared over r is equal to bqv, the magnetic force, and then we will be able to calculate r and then calculate difference. Okay, so over here, first of all, the charge. For the deuteron, the charge is 1 positive charge, so that is times 10 to the negative 19, and then the voltage is 1 times 10 to the 4, and that is equal to the half mv squared. So I'm just going to do the entire half mv squared because this is just directly, we can directly substitute the entire thing into it. So over here, that will be equal to times 10 to the negative 19 times 10 to the 4, and then that is times 2. So that is equal to 3.204 times 10 to the minus 15, and then we input this into the second equation. So over here we have 4 times 10 to the minus 15 over r is equal to that is 0.5 Teslas times charge. Okay, so the charge and then times the velocity. Oh, okay, so we have to calculate velocity. So we extend upon this. So v will be equal to the square root of this entire thing divided by m. So v will be equal to that is so it's and no, going to square root first and then over the mass. So the mass, the atomic mass unit. The atomic mass unit is 1.661 times 10 to the minus 27. Yeah, and then because and then we time it by 2 because it's the deuteron. So that will be 9.821 times 10 to the 5 meters per second, and we substitute this back in, and then we can calculate r. So r will be equal to these two things divided, so that's 3.204 minus 15 over this entire thing, so that's 0.5 times the elementary charge, and then times the speed of the deuteron, and that is equal to 0.0. I'm going to do 3 significant figures, so that is 407 meters. Okay, so this is the deuteron, so let's label it as RD. And then we can do the exact same thing for the proton. And yeah, so the only difference is just the velocity. Yeah, the difference is the velocity, so we can use the same mv squared because they have the same charge. And so yeah, let's do this over here. The velocity of the proton will be equal to this thing as 3.204 times 10 to the this 10 to the negative 15 over the mass of a proton, and that will be equal to, so over here 3.204 minus 15 over the mass of a proton is given as 1.673 minus 27. Okay. Slightly faster than the deuteron, so that's 1.384 times 10 to the 6 ms minus 1, and then we can put this into the equation. So the equation on the left side is just the same thing. Over r is equal to, and then 0.5 times the elementary charge, so that's exactly the same thing except the speed. And so therefore we can calculate r for the proton, and that will be equal to 204 minus 15 over, this is elementary charge, forgot a dot over here, minus 19, and then times the speed, and that is equal to 0.0289 meters. And now we can calculate the separation. So the separation, I'm going to say like delta D will be equal to the difference between the diameter of their circles, right? The diameter, yeah. So this is 2 radius, And then, so yeah, difference between their diameters. And then that will be equal to 2 times R d minus Rp. And that will be equal to, so that's 2 times RD is 0.0407 minus Rp, which is 0.0289, and that is equal to 0.0. I'm going to leave it for two significant figures, okay, so that will be 24 meters, and that will be the answer to the question.